Hi everyone, this is Safa and welcome back. In the previous episode, we simulated the linear motion of an autonomous underwater vehicle. Today, we will move from translation to rotation. Specifically, we will study motion around the vertical axis, known as yaw motion. Yaw plays a fundamental role in navigation and heading control because it determines the direction in which the vehicle is pointing. We will build a simple mathematical model, implement in MATLAB, and analyze the resulting yaw angle and yaw rate. In three-dimensional motion, yaw represents rotation around the vertical axis. When an AUV turns left or right, it is performing a yaw maneuver. Yaw is one of the most important variables in underwater navigation because it directly affects vehicle heading. The model yaw motion will start with a simple rotational dynamic equation. Here Iz is the rotational inertia, M is the applied moment or turning torque, D represents rotational damping, and R is the yaw rate. The second equation tells us that the derivative of yaw angle is simply the yaw rate. Okay. We begin by clearing the MATLAB environment to ensure a clean simulation. Next, we define the physical parameters. Iz represent the rotational inertia of the vehicle. The damping coefficient models resistance to rotational motion. And finally, M is applied yaw moment that causes the vehicle to turn. We define the simulation duration and the numerical integration step size. We allocate memory for the yaw angle and yaw rate. Initially, both quantities are set to 0. Okay, simulation loop. Here, the simulation loop updates the system state at each time step. This loop represents the evolution of the vehicle over time. Here we calculate angular acceleration. The applied moment attempts to rotate the vehicle. Rotational damping opposes the motion. The net moment divided by inertia produces angular acceleration. Using Euler integration, we update the yaw rate. The new yaw rate depends on the previous yaw rate and compute angular acceleration. Once the yaw rate is known, we integrate it, obtain the yaw angle. This is equivalent to accumulating rotational motion over time. Here, MATLAB computes the yaw angle in radians. For easier interpretation, we convert the angle to degrees. And finally, here, we visualize both the yaw angle and yaw rate responses. At this point, we have translated the yaw dynamics equation into MATLAB code. Let's run simulation and observe the rotational behavior of the vehicle. Okay, run. You can see AUV yaw angle and AUV yaw rate. The yaw rate starts from 0 because the vehicle is initially stationary. At the applied moment accelerate the vehicle, the yaw rate increases. Over time, rotational damping grows and reduces acceleration. Okay, eventually the applied moment and damping balance each other, producing a constant steady state yaw rate. Okay, and here the yaw angle continuously increases because here you can see the vehicle keeps rotating. Initially the curve is nonlinear because the yaw rate is still changing. Once the yaw rate reaches a nearly constant value, the yaw angle grows approximately linear with time. Okay. Notice that the yaw angle exceeds 360 degrees. This is completely normal because we are tracking the accumulated rotation of the vehicle rather than limiting the angle to a specific range. Okay, today we built our first rotational model of an autonomous underwater vehicle. Starting from a simple yaw dynamics equation, we simulated both yaw rate and yaw angle using MATLAB. Understanding rotational motion is essential because nearly all navigation and heading control systems rely on these concepts. In the next episode, we will continue expanding our vehicle model and move on a step closer to realistic AUV dynamics. Thanks for watching, and I'll see you in the next video.